What's wrong here? 2 water levels? Well, that's just an out-and-out fake. You know that water seeks its own level. That's just common sense.
Were you surprised at what you saw? Here was something which in fact flatly contradicts common sense. Well, why not? Do you think perhaps that common sense is always right? A scientist knows it isn't. But then everybody knows a scientist has no common sense. Should we conclude then that common sense has nothing to do with science? Surely that's an extreme thing to say. What actually is the relation of common sense to science?
First, we'd better agree on what we mean by common sense. I take what may seem the odd view that common sense is that human capacity to order and assess past experience in order that it may be projected into at least some ability to foresee the future. Common sense of this sort begins to develop in each of us at his mother's knee. And it is only by the exercise of such common sense that you can foresee the events for which you must prepare yourselves if you are to survive. Now, common sense is not reflective or explanatory. Its maxims are rules of action with which we face the problems of everyday life. And common sense is fragmentary, unorganized. It makes no attempt to reconcile such maxims as look before you leap, and its direct contrary, he who hesitates is lost. Science has been called organized common sense. And the description is not unjust if we make due allowance for the drastic transformation produced when you organize the intrinsically fragmentary findings that are the end product of the operation of common sense. Surely the same urgent search for a rational order in experience looms large in science. For to survive, science, too, must use past experience as the basis for predictions of the future. Science justifies itself, proves itself by this ability to predict. To predict not merely the month and day, but even the minute and second of an eclipse. To predict what will happen when masses of pure graphite and uranium are suitably juxtaposed in an atomic reactor. Thus, in its intent to organize past experience as a guide to the future, science is exceedingly closely related to common sense. But in science, the fragmentary organization of experience provided by common sense is carried on to a much higher level, to a much more comprehensive organization. And in seeking such an organization, scientists often find it necessary to invoke new ideas, new concepts, new principles that are not in keeping with what common sense takes for granted. That is, scientists will not hesitate to resort to novel constructions suggested by a disciplined but freely ranging imagination if they find that only thus is it possible to fit their facts together to develop a comprehensive rational order in experience. Let's look at a particular case drawn from history. Let's see how scientists came to grips with a series of phenomena that merely as facts seem to fly in the face of common sense. A syringe. The plunger moves readily when this end is open. I close the end. This plunger no longer moves very readily if I manage to budge it it springs right back to its original position. Why? Here, colored water will move from one vessel to another. That's all right. Water seeks its own level. But what holds the water up here in the tube? Why does not it, too, fall down this common level? Why doesn't the water fall out of this bottle? Or out of this tube, which is some 3 feet long and wide open at its bottom? Some 2,000 years ago, men began to separate certain phenomena of this sort from the great mass of other puzzling effects presented by nature. Such phenomena were separated, grouped, brought into an orderly relationship with one another by means of a theory that seemed to explain them all. But make no mistake about it, some quite uncommon sense, a real imaginative flash, went into the making of the first theory that comprehended phenomena such as these. This theory pivoted on the concept of a vacuum, a void, a space totally empty. There is here no simple, familiar analogy. Nobody had experienced a vacuum. Even a poor one could not be achieved until some 1,000 years later. For all that, the ancients did arrive at a fairly persuasive theory, a theory that today we epitomize in the statement, nature abhors a vacuum. And obviously, if a personified nature abhors a vacuum, then by an analogy drawn straight from human experience, she ought strenuously to oppose any process that involves the formation of a vacuum. So using this theory, you can see quite readily why it is difficult to pull this plunger back if the end is closed. To pull it back would be to create a vacuum. Nature opposes that. Open the end. No vacuum need then be formed since air can enter, and of course, the plunger moves very readily. If the water were to fall from this siphon, there'd be a vacuum up in here. Nature does not permit that to happen. If the water were to fall from this bottle, there would be left something approximating to a vacuum. Here, then, the abhorrence of nature for a vacuum sustains the water at a level 8 inches above that in the trough. And in this tube, that same abhorrence maintains the water at a height of some 3 feet. Presumably, the same would be true if the tube had been 10 feet high. It would have gone up 10 feet. If the tube had been 100 feet high, it would have risen 100 feet. Now observe, this simple theory ties all these phenomena together, fits them into a rational order. Indeed, all the individual observations might now safely be forgotten, because they can all be reproduced as logical deductions from the theory. The theory pivots on the totally imaginative concept of a vacuum. But as a good scientific theory should, it summarizes much past experience, and even more important, can point the way to new dimensions of experience. For example, suppose you had never observed it. You might still predict that water could be lifted with a syringe. Water hastens up the tube to fill the vacuum that would otherwise be generated by the withdrawal of the plunger. Having gone this far, it's not too difficult to see how a modified syringe device, provided with appropriate valves, can constitute a lift pump. Here is such a pump. There's a plunger that moves in its center. There's a valve here and a valve here. Watch the plunger and the valves. On the upstroke, the upper valve remains shut, but the lower valve is opened by water flowing up to fill the vacuum that would otherwise be generated by the withdrawal of the piston. On the downstroke, the valve positions are reversed, and the water passes into the space above the piston, whence, on the next upstroke, it passes through the spout. From this laboratory toy, you pass to a working pump of great practical value, like this one. The theory that nature abhors a vacuum met the only criterion we have, prizing a true scientific theory. It ordered and explained past experience. It predicted new elements of future experience. Here's an analogy. Suppose these blocks represent the sort of experience comprehended in the sayings of common sense. Each stands by itself. Then a theory that fits these separate individual blocks together. So, it ties the blocks together, it organizes them. Holding the theory, we feel that we comprehend the blocks. We have them all at once. This theory may not be in keeping with common sense. It transcends common sense to do what common sense cannot do, to find a comprehensive order in experience, and to indicate new elements of possible experience, the lift pump, a new fact which hangs very well from our theory. As other kinds of facts are collected, individual, separate, unorganized, they too may be related to each other by another theory. And then, if we are fortunate, we may find some still larger theory which fits all these things together, like so. And so on and on in a great pyramidal structure. Now, the theory that nature abhors a vacuum looked like a pretty good theory for something of the order of 1,000 years. And then about 350 years ago, there came a somewhat disturbing observation. Lift pumps were then still quite crude, but artisans well knew that even their best pumps would lift water no higher than 34 feet. Hearing of this limit from a workman, Galileo became the first to recognize that this was an intrinsic limit on the power of lift pumps, that it was not merely a practical limit set by imperfections in existing pumps. And this conclusion was neatly confirmed when, in this same period, men constructed what we would now call water barometers. A glass tube more than 34 feet long, sealed at one end, filled with water, stoppered at the other end, and then inverted, as you see here, in a tub of water. The stopper then being removed. We formerly predicted that in such a tube, however tall, water would remain suspended to the top. But this is not what happens. The water level in the tube immediately drops to some 34 feet. 34 feet, the maximum height to which a lift pump raises water. Obviously, then, as Galileo had surmised, this height has some significance that transcends the flaws in pumps and piping. What could that 34-foot limit mean? Do you at once conclude that the whole idea of horror of a vacuum is false? Surely not. That theory beautifully explained the phenomena. It just wouldn't be common sense to give it up. Will you then say that nature has an abhorrence somehow neutralized by the opposition of 34 feet of water? But that would be entirely arbitrary. There's no other support for such an assumption. What then shall we do? Might we be able to learn something from the behavior of a liquid different from water? Preferably one drastically different from water. For example, the liquid metal mercury. Now, mercury is a pretty heavy metal. Perhaps I can show you that. Here is 1 volume of mercury, which I'm going to pour into one of these 2 cylinders, approximately balanced. The weight of the mercury forces that side of the balance down. Now let's see if we can balance it with water. We can put in a volume of water. Doesn't balance. We'll put in 10 volumes of water, and it still does not balance. 13 volumes, still no balance. But now, someplace between 13 and 14 volumes, we balance this 1 volume of mercury. That is then, volume for volume, mercury is approximately 13.5 times as heavy as water. The idea of using mercury in a barometer occurred first about 1640 to a young associate of Galileo's, Torricelli by name. Here's Torricelli's experiment. A 3-foot tube sealed at one end, filled with mercury to its very top and open here at the top. I put my thumb over the top and then, dexterously we hope, invert it in a pool of mercury. What happens now when I remove my thumb? Watch. The mercury falls. And what is left in the top of the tube? Might this region be empty? Could it really be a vacuum, that which had been supposed not to exist? Torricelli observed that if you tip the tube, the mercury runs up it without meeting any resistance. Nothing then at the top of the tube resists the motion of the mercury. That looks as though the top of the tube might indeed be empty. It's possible to confirm this tentative judgment even more strikingly by adding water at the bottom of a barometer set up exactly the same as that which we made ourselves. Mercury at the bottom, water layer floating on top of it. And now I propose to pull this barometer tube up out of the mercury into the water. Let's see what happens. The water rushes up, displacing the mercury, which falls down toward the bottom. And ultimately, if we're fortunate, we can fill pretty nearly the whole tube. It fills the entire space, and you can surmise that the space at the top of this tube was originally a vacuum. Torricelli went on then to show that mercury stands at the same height in tubes with either large or small vacuum spaces, and that in all cases the height of the mercury column is 29 inches, very nearly 2½ feet. Now what do you make of that? Remember that volume for volume, mercury is 13.5 times as heavy as water. And then it may burst in upon you that 13.5 times 2½ is just about 34. In other words, the heights in the mercury and water barometers are such that in tubes of equal size, of mercury and water suspended are exactly the same. The height of water in the water barometer is to the height of mercury in the mercury barometer as 34 is to 2½ which is the ratio of 13.5 to 1. Now here, surely, there is something more than mere coincidence. What does it mean? Torricelli found an answer. Indeed, he probably had it already in mind when he began his experiments. Observers of this period had seen that water barometers showed irregular fluctuations of height that seemed somehow correlated with weather conditions. This totally unforeseen observation suggested that the suspension of liquids in tubes might depend not on the vacuum or anything else inside the tube, but on something which, since it varies with the weather, is outside the tube. That would be a common sense inference. But common sense does not suffice to tell you what, in all the world outside the barometer, is responsible for the variable rise of its liquid. What can this something be? It varies with the weather, that is, with the state of the atmosphere. Well, what about the atmosphere itself? Could anything as tenuous as air produce the large effects you have seen? Could one imagine a sea of the air lapping around this earth of ours? A sea consisting of a very light fluid, but a sea of immense depth, with its bottom resting on the surface of the earth. Could the pressures in such a sea produce the effects you've seen? Superficially, at least, this is a preposterous analogy. First, how can anything as insubstantial as air maintain the weight of the 15 pounds of mercury that fill a 1-inch tube to a height of 29 inches? Second, and still worse, if you do suppose that the air can exert a force of 15 pounds per square inch, then you must allow that the force exerted by the atmosphere on the surface of your body is of the order of 15 tons. Surely it is not common sense to suppose that, all unknowing, you've been walking around under such a crushing load. Over such difficulties as these, Torricelli rode roughshod. After all, fish do live deep in the ocean, under what we may suppose to be enormous pressures. Torricelli and the more gifted of his contemporaries recognized that, for all its apparent implausibility, the concept of an atmospheric sea offered a new explanation for all the phenomena previously explained in terms of nature's abhorrence of a vacuum, and in addition, for those not well explained in such terms. The effects you saw over here are not due to horror of a vacuum, which might be formed internally, but to the action of a large external pressure that is not counterbalanced internally. The water is not sucked up by the syringe or by the pump, but driven up by external pressure. The same thing applies to water in the water barometer and the mercury in the mercury barometer. And since this external pressure is limited, you can readily understand why the rise is limited also. Limited to 34 feet of water or 29 inches of mercury, these representing equivalent forces opposing that exerted by the atmospheric sea. Here then is a new theory based on a new model, the atmospheric sea. And now if, in fact, we do live in an atmospheric sea, then if you ascend in this sea from its bottom, the surface of the earth, you should move into a region of lower pressure. To do this, you could climb a mountain. And when, within a few years of Torricelli's work, a barometer was carried up this peak in France, it was found that in the course of an ascent of some 3,000 feet, the height of the barometer did indeed fall about 3 inches. Thus, one salient prediction founded on the new theory was triumphantly verified, and many other such predictions have since been confirmed. And now, observe. This new theory, Torricelli's theory, pivots on a concept, that of the atmospheric sea, which is the fruit of a lively imagination. Just so did the older theory pivot on a concept, that of the vacuum, similarly remote from everyday experience. But observe further that both these theories have this in common with each other and with common sense itself. They impose a rational order on past experience, and they successfully suggest and explain important new elements of experience. Thus it can be seen that when scientists import into their theories imaginative, speculative, apparently far-fetched concepts, the void, the atmospheric sea, atoms, electrons, quanta, they do so only because of the imperiousness of that need to order and rationalize experience, which is the motive power of science and common sense alike. What are we going to say when science and common sense appear to be in conflict? Observe, there's nothing magic or sacred about common sense. The old saws of common sense are often nothing but ancient assertions of science. Later, with an enlarged experience, some of these became more difficult to maintain and were ultimately abandoned by scientists in favor of more sophisticated concepts. And these concepts, originally thoroughly speculative, extravagantly imaginative, become in time part of the working body of common sense. Our round Earth. At one time, nothing in science seemed so absurd as the supposition that there are people who live upside down with their feet above their heads. An intelligent man of the Middle Ages had no reason to credit such a ridiculously speculative idea. But you, who have lived with the idea for years, you who have friends in Australia, you regard the speculative fancy of a round Earth as a matter of common sense.
You have just heard Professor Nash give you his account of the relation between science and common sense. On other programs of this series, you may have heard or you may hear other physical scientists whose views on this matter are in lively opposition with those of Professor Nash. I believe that in this way you will obtain from this series a much more truthful view of science and scientists than if you had been presented, after careful selection and exclusion, with an artificial picture of a group of scientists without ever a shade of disagreement between themselves. By sticking to the facts of the case, as for instance that mercury rises some 30 inches in a barometer, school textbooks give you a non-controversial but admittedly dry and uninspiring view of physics. The instant we try to appreciate what the discovery of this fact may mean in a broader human context, differences of opinion appear. As soon as scientists stop making measurements and start talking, they become human again and disagree with each other. You will have more than one occasion in this series to observe that, in spite of their abstract theories, scientists are human after all.
This is National Educational Television.